about embedded logical channels in GKP error correction. This is still a work in progress. We are working on finalizing the results, and hopefully we will put it out soon. This work is in collaboration with Jonathan Conrad and Ben Bargiola, who is one of the organizers of this workshop, and Rafael Alexander, who is now present in this room with me. Yes. So, yeah, what is the main goal of this research? We want to construct a mathematical formalism for describing CV effects within GKP subspace in terms of qubit channels, considering the effects of realistic GKP error correction. And then what we do with this formalism, we use it to see how much any CV noise effect affects our logical encoded information per time step. For example, we can define Pauli transfer matrix for CV noise per time step. So there has been some work towards studying CV effects in terms of qubit channels using GKP error correction. Here are two examples. There might be more too. In this work by Mahnaz Jafarzadeh and collaborators, which just came out last year, they assume that they have access to the ideal GKP error correction, and they consider what's the best they could do if they had access, for example, to loss followed by a perfect error correction. So their work turns out to be quite interesting. However, physically, you don't have access to an ideal error correction. So what we do, we add one more level of complexity. We take this to a physical domain, and I'm going to show you a physical or realistic GKP error correction where we have finite energy ancillas, and we'll see that we can still define qubit maps and qubit channels. However, because of this noise on our ancillas, so we are going to have to introduce a mathematical technique to be able to define qubit channels. And that's what this research is all about. So I'll briefly introduce GKP code space. The GKP code is a bosonic quantum correcting code to encode the logical information in an infinite dimensional Hilbert space. In their ideal form, they are defined as Dirac delta combs with 2 root pi spacing in position. And they logical state 0 has peaks in even integer multiples of root pi, and state 1 corresponds to odd integer multiples of root pi. So this state in the ideal form is not physical because it has 2 infinities. It is infinite sum or infinite superposition of infinitely squeezed delta functions. However, in practice, you have to use physical states. And one way to approximate a physical finite energy state is to take each of these delta functions and replace them with a Gaussian function, and then multiply this with an envelope with a Gaussian shape. And what it does, it kills the state for higher values of quadrature. So these t's are no longer infinitely seen, and they don't go on forever. And these effects are captured by envelope operator, e to the minus beta number operator, which is also called pocket damping operator. We will refer to this state as a physical state, and then now let's come up with a model to for GKP error correction using this finite energy states. So here is the teleportation circuit that implements GKP error correction in optics. So starting on the left, we have a physical state which contains our logical information, and we introduce 2 finite energy ancillas. We apply beam splitters, these arrows, and then do homodyne measurements on the input state along with half of the GKP bell peg. and then conditioned on the homodyne measurement outcomes, which give us the syndrome data for GKP error correction, we do a logical correction. So in this teleportation circuit, none of the states are infinite energy. That's why this is a model for finite energy GKP error correction. And here are Q0 states or sensor states, and they are like GKP plus state, which is rescaled by root pi in Q or 1 on root pi in P, so that it has square root of 2 pi spacing in both Q and P direction. And the reason that we introduced these two states is that it has been shown in this paper that if you send two sensor states through a perfect balanced beam splitter, it becomes deterministically a GKP well pair. So, and these N operators here indicate envelope operator. Now, we'll use some circuit identities to find Kraus operator for this GKP teleportation. This circuit is identical to the one right here, where we have replaced measurement outcomes with displacements right before the detectors, and then we commute them with the beam splitter in a way that it acts only on the first mode. And then we commute these two noise finite squeezing operators with beam splitter. Then we use a nice property of maximal entangled state, where if we have a local operator acting on one mode of a maximal entangled state, you can move it to the other mode by taking the transpose, and the resulting two-mode state is identical to the original state. So this is called this operation is called bouncing. So what we do to get to this circuit right here is that we now bounce this N operator to the first mode. So now what is left here is just an EPR pair, projection to an EPR pair. And what we have in this yellow box is nothing but an ideal CV teleportation, which does nothing to the state, just move it from the first mode to the third mode. So this whole process is described by this CV Kraus operator here. So what this Kraus operator does to the state is, if you apply it on a physical state, the state gets displaced by an amount which is conditioned on the homodyne measurement outcomes, then gets hit by an operator, which takes state out of code space. But then later, when we apply code space projector, you are again back to the code space. However, there is another N operator that appears after code space projector that takes you again out of code space. So at the end of this circuit, you are not in the code space. And that's a problem. That means that there is an information leakage. So this information leakage is already a problem, but there is also an extra problem. And that is, this leakage is state dependent. Why? Because, so in addition to those two effects that I mentioned in the previous slide, envelope has one more effect, and that is it takes the peaks and shifts all of them slightly towards the center. And because different GKP states have different support in the phase space, so the amount they leak out of code space is different. So that's going to cause a problem. I'll come back to this later again. So now we want to see how we can address these challenges so that we can define logical qubit to qubit maps. So the solution that we propose is that if you consider multiple runs of teleportation circuits, and if you chain them in a one-dimensional fashion, so you'll have code space projector And then if you focus on the piece that appears in between two projectors, you can define a qubit to qubit map such that it takes as input a qubit state and outputs a qubit. So we established the correspondence between the whole CV evolution and a qubit map. But now there are some terms left over in the beginning and the end of this evolution. So qubit maps don't span from the beginning to the end. So to realize these leftover terms, we are going to take into account state preparation and readout measurement into the overall scenario. So suppose we want to prepare this logical state where these P bars are GKP logical Paulis and R's indicate block vector elements. However, in practice, we prepare a finite energy state with N indicating envelope in this formalism. So, and also, imagine a scenario where we end the chain of teleportations with a destructive readout measurement in a logical Pauli basis. And to perform this readout measurement, what we do is we supplement our encoded state with a beam splitter to the circuit. Here N indicates the finite energy effect on our encoded state or ancillas state. And then we measure in Q and P. And then using some circuit identities, you can show that this is identical to implementing a displacement conditioned on the final homodyne measurement outcomes, and then followed by a noise or an operator before doing a readout measurement at the end. And this whole process is described by POVM element here. So the measurement outcome is a complex number, and we divide this complex domain into two disjoint sets, and that allows us to treat this as a logical readout measurement. If we measure and get any value, which is in this set, omega naught, we interpret that as our logical zero. And if we get any value in this set, we interpret that as our logical one. Now we want to add these two to our overall evolution so that it allows us to embed this first and final qubit map as well. Now you see that on the far left, we have a logical input, and on the very right side, we have a logical output, and whatever in between are just qubit to qubit maps. So that is great. Now we defined qubit to qubit maps, and it looks like it should work now, but there are still challenges with this qubit maps. And remember that I said this leakage depends on the state. So that's gonna cause problem, and we'll see that these qubit maps don't satisfy all the properties of a legitimate qubit channel. So we defined these qubit maps by starting from a CV evolution. That evolution satisfies the following properties. The global CV evolution, if you average over a syndrome, is a CPTP evolution. So it is a true channel. And then you can decompose this global channel into local channels that are also CPTP map. However, this CV evolution doesn't preserve the code space. So what we did, we defined our qubit maps, which preserve code space, but they don't have these properties anymore that CV maps had. They are not globally trace preserving, and also they are non-Markovian, meaning that we cannot decompose them into local maps. And why we care about decomposability, it is important because we can define local qubit evolution, and that allows us to see how much, to determine local error rate per time step, and that allows us to optimize the GKP decoder also per time step. So we want to find something that both preserves the code space and also has all the right properties of a qubit channel. So there is a way to do so, and what we do is that we take an operator or envelope and we replace with a randomly displaced version of it. But these shifts are, note that, yeah, these are Pauli's, which are shifts by root pi. And J and K are chosen from a minimal set such that we make sure that we cover all the possible shifts along all the possible different directions in the phase space. So in other words, you can think of it in that way. So instead of having a logical state where you have an envelope which is always centered around 0, you have 9 different envelopes that they have been shifted by root pi along different directions. And later you'll see that if we average over these 9 possible approximate states in a particular way, we can recover the properties that we would like to see in our qubit maps. And also note that in the regime that we have a high quality state, meaning this envelope or an operator goes to the identity, then PP dagger, just they cancel. So this approximation won't do anything, meaning in high quality regime, these all states are still a very good approximation of each other. So what change this makes in our teleportation circuit is that we have the same teleportation circuit. What we've done, we have just replaced n operators with their shifted version. Now we want to see how this modifies our qubit maps. So remember, the way that we defined our qubit maps is that if you do this teleportation twice and you take the piece between 2 code space projector, you can define qubit to qubit map. So now we have the similar expression for our qubit map, except these n operators have been replaced with their shifted versions. Now we need to define a rule for these x's, which represent the center of envelopes, so that they satisfy all the right properties of a qubit channel. So what we do is we define 4 random bits per time step, and then we choose x's in this way, which will lead to a correlated twirl, and we'll see this now. So what we get by this choice for the x's values or for the center of envelopes is if you average over gamma and delta, that will perform a correlated twirl between CV time steps. And from the qubit perspective, what that twirl does is it makes the map to satisfy this property, meaning that Q dagger Q, if you average over gamma and delta, is proportional to identity or GKP projector. But this proportionality depends on mu's. So that we cannot average over mu's. That's what leads us to do another average, and that's average over epsilon and phi. What this average does is that it performs a twirl, which lets us to make the qubit maps to be time local, meaning they depend only on a single mu. And how do we do that? Is that okay, we want to move this logical correction or GKP shift operator to the left and include that in this blue box so that our qubit map will be dependent only on mu's from one time step. And we want to do similar thing here. If we move this one to the left, then we can include that as a part of previous qubit map. But the problem is that it has to commute with an operator. So how do we make it to commute with an operator? Is that first, for each mu, it is mapped to a logical Pauli by this F, which is defined by decoder. And so each mu is mapped to either identity X, Y, or Z. But then we have options, different options for each of these logical operators. So we can do shift, for example, for X operator, we can shift it along to the right or to the left, or for Z operator, we can shift it up or down. So which one we need to do? So it turns out that if we correlate this sign with epsilon and phi, and then average over these two bits, then we can make this logical this displacement to commute with the N operator. So the GKP shift operator that is implemented at the end of each teleportation circuit is equivalent to applying an ideal GKP Pauli right after the code space projector. Now we have all the pieces here in this blue box, only depending on mu from one time step. So we made our map to be local. And then what we get as a bonus is that turns out that if you do both twirlings together, you can remove the dependence of the syndrome on the logical information. And that's an extra thing that we get with using this technique. So what we achieved with this formalism is that we defined a qubit maps, which are CPTP, so meaning that they are genuine qubit channels, and they satisfy these properties. So our qubit evolution agrees with the CV evolution, and we can decompose this global qubit evolution into single time step CPTP qubit maps. And what that means, as I explained earlier as well, so you can compute single time step Pauli transfer matrix, for example, and then the global one, you can just find the PTM for that by doing a matrix multiplication. And also, this technique helped us to eliminate this logical leakage, so that the probability of syndrome at each time step doesn't depend on logical information anymore. So this formalism works for any decoder. So remember, we didn't specify what decoder we use. So it works for any time local decoder. And also, we can extend this to include noise channels such as loss that happens between GKP teleportations. Then we can see how it affects, like in terms of qubit channels, how it affects our logical information. Thank you.
Thank you very much, Mahnaz.
Yeah.
Are there any questions? So you cannot see what's going on, but I'm passing a microphone around for the questions.
Okay.
One.
So you use this twirling strategy to make a much nicer, like theoretical description of the effect on the logical qubits. I'm curious if you're proposing this twirling strategy as something to actually build in a quantum computer, or is it a theoretical tool just to understand the noise?
So yeah, that's definitely just a mathematical tool, a theoretical tool to understand the effect of various CV noises on our logical information. And the approximations that we have done here is that we approximate the teleportation with its twirled version, meaning that instead of having a fixed GKP bell pair, we create bunch of those GKP bell pairs with those envelopes that I explained, and then we average over them. So what we do with this is to approximate our untwirled or the original teleportation that is done in the lab with twirled version. And the other approximation or restriction that we have here is that after generating GKP bell pair by sending finite energy sensor states through a beam splitter, that operator that makes the state finite in energy remains local. So in the regime that these two approximations hold, we can define exactly qubit map that has the same effect as our CV evolution. Raf wants to add something.
It doesn't have to be, N doesn't have to be the photon map.
Yeah. So yeah, we can on the first mode that we use for as our input state to the teleportation circuit, we can have any type of noise map.
Thank you, that's very helpful.
Sure.
Are there any other questions? There's one here.
Hi, great talk. I was just curious, have you got some intuition about what the correlated twirl would do to, particular channels? It's sort of hard to have some sort of, I mean, is there any graphical picture you can give us of what the correlated twirl is doing?
So yeah, so this correlated twirl, what it does, as I explained, it happens because of averaging over gamma and delta. And that averaging over gamma and delta makes our noise channel to be diagonal in Pauli basis. And if you don't do this type of correlated channel, so you won't be able to recover the properties of a CPTP map. Does that answer your question?
Yeah, thank you.
Sure.
Are there other questions? There's one more.
You gave all of this treatment in terms of the teleportation style of error correction. Does it all apply exactly the same if you're doing the steam style of error correction?
So the reason that we could use this formalism was because of the code space projector that appears when we use teleportation-based error correction. That's the nice property of this nil error correction scheme, that when we use this circuit in optical implementation of it, like if we have beam splitters, so there is a code space projector there, and that projector is what allows us to define these qubit to qubit maps.
So you think it does not apply if you use the steam error correction?
Yes, no, it won't.
Okay, thank you.
Sure.
Any final question? Okay, if not, let's give Mahnaz a round of applause.
Thank you.